Okay. Well, thank you. I'm really, really happy. These are my favorite kinds of talks. So first, let me see. I can move my slides. Let me just say a tiny bit about me. I'll be quick. I was born in Argentina. That's a piece of my city, Buenos Aires. I went to school in my city, like we usually do in Argentina, and this was a long schooling, only math. I think you had the same type of programs there in India. Then I went to Spain to do my PhD in Barcelona. And now I'm an associate professor at Stony Brook University. I don't know if you can see me there. I'm standing in a green dress. I work a lot with undergraduate students and research too. And those are two of the students who did some work. And I'm a frog in mathematics. I don't know if you heard that classifications. Mathematicians are divided, I think it was Morgan Dyson who said, between frogs and birds, and the frogs, know a lot about a small problem, and they know every piece of stone, everything about it, and the birds over blue and, see structures. Well, I'm a problem solver. The movie that you just made is something that, I share, we all love around here, Somnath too. It's one of I made the animation, I'm very proud of it. Type of things I am interested in. Here it is. I like to visualize math, and this is one of the things I will show you. A torus divided into many regions with fantastic mathematical properties. And recently, about 3 years ago, I started to study math history, and I'm working on the life of a fantastic mathematician, Alicia Bull, whose picture you see there. And she studied geometry in 4 dimensions. And one day I can give you a talk about her. She is out of the charts. So I wanted to say, well, I'm not very good. I never use Google, so I don't know how it works, but I tend not to see any chat. So if you're going to send me a chat, somebody has to help me and say words with sound, because please feel free to ask questions. That'd be fantastic, but don't expect I read them at least with no delay. Okay, so well, let's start. So surfaces. Please also feel free to ask questions. I don't know. I hope it's fine. Sometimes tell them how to. Whatever, people probably can unmute yourself and ask questions.
Yeah, I'll do that. So in fact, if they send in a chat, I can read it out to you. So it's
perfect.
No worry.
Perfect. Yeah. Perfect. Oh, you can. People can interrupt. I am very interactive, even in Zoom. So I'm happy to answer. So here is an example of a surface, and we have to think, that this is we could think of the outer layer of this object. In this case, it's a sphere. And there's this very old topology joke that says, from the topology point of view, these two things are the same. And what it means is, well, by same, this is a great thing at math. We just say what we mean by each word. Same means we can deform continuously one into the other, roughly speaking. Here is another surface that can be deformed also, again, in the outer layer of this is, as you know, as a donut, an American donut, or a torus. Here I have more examples of surfaces, and they are all deformable one into the other. And here I have even more. And here I have a fourth one. This is not deformable into the other 3 that we have there. And here we have another kind of surfaces. These are still surfaces for me, but they're different from the previous one. The previous kind that I show you, here it is. One more. And the difference here, I see the 2 kinds together, left and right. The difference is that the surface on the right have boundary. If you see here, can you see? Yeah, you can see my mouse, I can see. So this is a boundary. So I will use surfaces with boundary sometimes later in my talk. But these are, our main characters. And you probably know that, surface can be orientable. One definition is that a surface orientable if it doesn't contain a Möbius band. If it's not a Möbius band inside the surface. And the Möbius band, I have several examples here. And here what you see is that the ants, are walking on the Möbius band, and they can start on the top and keep moving, and end up at the bottom of the same position they are there. And since we're here, maybe I should ask you something. I need one of my props. See ya. And now maybe some of you can highlight me. And this is a question for students. Is this a Möbius band? Look at me, look at I'm showing you something in my little screen. I don't know if you can see it.
Yeah, so somebody wrote yes, yeah.
Yeah, no, I can, yeah. Come on, I mean, there's 51 people, nobody asks. Vote, you know, from Argentina, there we have to vote. It's mandatory, or you get trouble in the taxes. So everybody should give your bet. It's a bet, okay? Math is about thinking. And if you think of yes or no, think why. And I have only 2 answers. Gee, I'm going to cry. So no. Okay, I'm reading now because I'm looking. Okay, it seems to be right. And again, if we had more time, I will let you talk, but I'm going to tell you it's not. And it really looks like it. And I tricked, many even famous topologists with this. But if you look at it, why is it not? Well, what is a Möbius band? I said it very fast, but one of the things I say is that, if I have an ant, exactly, somebody said the colors are off. If I have an ant, I'm trying to see myself and the chart is over me. Sorry, here it is. So the ant, if it starts walking here, the ant will go on the brown side. Look at my finger, it's here and it's moving around, and it will never leave the brown side. I said the brown finger, the brown side, because the brown side is totally continuous. So this surface has 2 sides, a brown side and a yellow side. If I show it to you, and there's never a moment where the brown and the yellow collage, they're crash. So here, I'll show you another example. So this surface here, it looks very similar to the previous one. I have a yellow and a blue side, and I'm covering something on purpose because here, the yellow and the blue, there's a crash. So here, the ant will be able to walk. And if you look at this carefully, I'm trying to put it, this is 1 turn. And the Möbius band is made by a strip of paper, as you know, doing 1 turn. This one has 2 turns. So it's like a minus, minus, plus. Here, this is not a Möbius band. This one is orientable. This one is a Möbius band. And another thing that the Möbius band has, if you see my Möbius band, in fact, here, this one, I could go around it with my finger, and you should try it, and I could run around the whole boundary without lifting my finger from the boundary. This one here has 2 boundary components. If you see, one is orange, and the other one is light green here, and there are 2. Anyway, you can ask me more if this is not clear, but one has to think why. And if you said yes, good, because you dare to answer and probably you understood. I mean, good if you understood. Okay, now, so surfaces, we have this big theorem about surfaces. Surfaces, I hope, showing you this, the pictures, they can be incredibly complicated. There's an enormous variety, twisted. I mean, try to picture in your mind all this, incredible amount of surfaces that one could draw. But they can be classified, divided into groups, and they can be deformable, say roughly, either into a sphere, or this one, which is a torus, or something with 1 handle, 2 handles, 3 handles, and so on. And if I allow boundaries, well, they can also be a sphere with 1 boundary component, 2, and then torus with 1 boundary component, and 2 handle, and so on, and then 2 boundaries, and so on. And this is a really fantastic, wonderful theorem. Again, if you think that surfaces are, can be really wild, and, but it's always one of this. this is the type of theorems that in mathematics we love because it helps us understand the objects we're studying. So now let's do about something with surface. So this is a question that one has to read with care. It's tricky. You read it and I read it. It says, what is the maximum number of regions you can divide a sphere into so that every pair of regions share a border that is more than a point? So they have to share a segment of boundary. And bueno, I'm asking for the maximum, but it's hard to answer the maximum in cold. So let's start to think, can we put 2? Well, 1 we put already. So let's put 2. And yes, here I have a picture where I put 2. I'm not having any prescription of what shape, any shape of regions. They have to be one block or connected. Can I put 3? Well, if I add one more region to the previous one, I see that this is 3. And for instance, you see that everybody, red and blue, share this segment. And the blue and green share this segment, and so on. Can I put 4? And hopefully you're thinking that because of time, I'll show you one of the pictures with 4. And if you check, every pair, say green and pink, share a segment here. Pink and red share a segment here, and so on. Can I put 5? And again, I could leave you here, but the answer is no. And I will try to say a little bit about why. So let's do something with these regions. Here is what I'm going to do. I have my 2 regions, and I'm going to put a point or a vertex on each region. And then I'm going to join the regions with a vertex if they share a segment. And then I'm just going to look at the vertices and the edge. And here I do the same thing. So here I have my 3 regions. I put point and look at what I get is called a graph. It's finally many vertices and edges joined together in the way you see there. And here I have the 4. And when you look at this is the graph of the 4. Well, if we were able to add one more region, I also should be able to make a graph, something like this, with 5 vertices where every pair of vertices share an edge. But the vertices cannot overlap. And why is that? So I repeat, vertices cannot overlap. Edges. Edges cannot overlap. Vertices cannot overlap either, but that's totally, obvious and not with consequences. The edges cannot overlap because, since they share the 2 surfaces, the 2 regions share a segment of boundary, then I can go from one vertex to the other, crossing that segment, and, the other segment cannot be there. I make them cross that segment. So what about the surface of a bagel? I show you a hint in the first slide. What is the maximum number of regions? We can do the same thing. If I could put the 4 regions that I put on the sphere, but in fact, the fact that the torus or bagel has more interesting topology means that I can divide into more regions. And here they are 7. And I'm going to put here is the graph. So this means I can do a graph with 7 points, and every pair of points is joined by a segment, and no segment intersect each other. And I'm going to show you, here is the 7 made in crochet. And if you're curious, I wrote a little article about how to make it. It's not that hard. And, I'd like to convince you quickly that everybody touches everybody. Everybody shares a segment of boundary with everybody. So say we're looking at this yellow region here. And, first, the yellow region, this was made in this way. First, I make this kind of cylinder where I put rectangles, one next to the other. So the yellow here is touching the orange and the green, the 2 neighbors. Then what I'm going to do is I'm going to, here this, kind of cylinder, hollow cylinder, has a peak in the top. They have these peaks and valleys in the bottom. So I'm going to twist this like this. I'm going to twist the top like this and hold it and make it fit one of the valleys here. One peak here is going to the valley. If I choose the appropriate valley, everybody will touch everybody. So if you see this here, for instance, the yellow, as I said, it touches two colors here. Touches means shares a segment. It touches two colors. This is like in one, in one of the extremes, two. And if I go on the other side of the rectangle, I'm trying to follow it, it touches other two. So 2 plus 2 plus 2, you probably know, is 6. And these are 7 regions. So each one touches 6. So everybody shares a segment with everybody. And this is a wonderful idea, the connecting, there's a lot of work on this is done by using this different ways of presenting the problems. Either I have the regions or I have the graph. These are like two different forms of the problem. And that's a great idea that we often use in math, translated thing, say something in very different ways because certain settings are better to see certain things than others. And here, this is I do sometimes a little propaganda in my talks. I didn't tell Somnath about this, but so this is an idea. I wanted to emphasize that idea. When I prepared this talk, this is a couple of years ago, I gave it somewhere else. I was trying to Google ideas, like I wanted the person with a little lamp. Every person I found was a white male. And I like white males, I'm married to one, but only the only person who had an idea about the white male, there was this girl, if you scroll a little, but there were no girls. And then I said, what, not a non-white girl? So I said, let's just create my own picture of, a person with a light bulb idea, which is not the standard one. So sometimes, this is what I'm saying, we don't have to believe all the images that are there, even if they are predominant. So, double bagel, how many? How many regions? Oops, I'm looking at my time and already went fast. Anybody wants to bet how many regions I can divide it by a double bagel into? Oh, I learned how, I'm seeing the chat now. Oh, okay, somebody put the answer, which is terrible. You put the answer. If you read somewhere, we're thinking here, yeah. So, and this is related to the 4-color theorem. And we are, it's 10 for the double bagel. Well, it's a good, it's a good bet because it's more. And I'll tell you the answer. The answer is 8. So this is the first picture that I know of that appeared. This is from a work of Tietze. The first, we knew that the answer was 4, but this is the first picture that appeared. It's quite complicated. And I made it here. I lost this one. I tried to copy it. But it turns out that there's another picture that I found, I think independently by Susan Goldstein, who's there, and a French mathematician whose name is evading me. And I'm going to tell you how it is. So this is how you do it, the 8. And I'm not proving the maximum is 8. I'll tell you in a second about that. But so this here is a torus or bagel, it's kind of fat at the end. And it has a boundary here. This is the boundary. So you have to imagine that this is hollow. And this circle here is the boundary. And if you check with care, every color touches every color. For instance, this pink touches this lilac and touches the red. And on the other side, it touches the purple. So everybody touches everybody. But also, the pink has a long boundary here, a long segment on the boundary, and on the other side, it has a short segment. So now I'm going to make another one of this. I already made it. And I'm going to feed them together. So look, I grab the pink one, and I'm going to make the pink fit. Oops, let me just see what I'm doing. The pink now is touching 3 colors. Sorry, I'm trying to if I see it, the camera doesn't. So the pink touches the green, the light blue, and the yellow. But on the other side, oops, sorry, it touches the turquoise. So the long boundary touches 3, and the short boundary touches the 4. And this shape here, everybody touches everybody. So everybody here touches everybody here, and everybody vice versa. So this is an 8-color genus 2 or 2 handles surface. What about a pedestal? So, let me tell you a story. So here, we knew that the number, sorry, I have a sneeze. The number was 9, but I didn't have a nice map, something that I can understand and explain easily, like I just explained, the one with 2 handles. And then some students, undergraduate students here that work in a little research project with me, found this fun one. And here is the first one I made. And I'm going to, here is one of the students with my crochet things as a hat. Here they're working. And this is their idea. What they did is, this is, again, a 7-color torus, like the previous one, a little thinner. But they put holes. These are 3 holes. In topology, I put them out because it was easy to make. So these are boundaries in strategic places. This boundary here, for instance, touches, the 3 colors landing there. This light blue, yellow, and dark blue. And then they said, okay, now I'm going to get a gadget like this. This is like a Y divided into 2 colors. And this one has 7 colors. This one has 2. And everybody in each of them touches everybody. Well, now I'm going to attach appropriately here, this in some way that I want to make the 2 colors of the Y piece touch, the 7 colors of the torus. And this gives us a surface with 3 handles. You have to think a little to see it. This was their work. And I'm going to skip they did the same, and I put a picture there for 4 handles. Now this is 10. They did the same for 11, and they did for the map of 12 colors in the 6-handle surface. As you see, it's quite complicated, but the idea is just get into torus and glue them in the appropriate way. So somebody put there the formula, and this is what it is. And, well, oops, something happened here. Oh, sorry, I have a problem with my slides. So it's funny because, when you do 7, can you see my mouse now? Oh, no, here. Okay. 7, the maximum number of regions is 12, but when you put 8, the maximum number of regions is, 6 is 12. And of course, this is we see a pattern. It seems like up to 6, we are growing linearly, but 7 is 12. So it's not linearly. And in fact, the formula is the smallest integer that is the largest integer, it's the largest integer that is smaller or equal than this number. Now, this number here is a solution of a quadratic equation, like a, like minus b plus or minus square root, etc., etc. And it can be found by playing, and I'm going to say words I'm not sure you understand, by the Euler characteristic of the surface computed with the regions. So the idea is you use the graph and you use the division of the surface and you have some property of the surface itself, and you find this number. Now, it's not too hard to prove that this is an upper bound, meaning that if you have a number of regions with this property that everybody, shares a segment with everybody, the number of regions has to be smaller or equal than this number. It's very hard to show that this is the best bound. Like, give an example for each, with this number of regions. Show that this is the best bound. That took many decades since the problems, and I may talk about the history of the problem, but since the problem was posed like in the mid 1800s, the solution came in 1968. So hard problem. And somebody mentioned the 4-color problem, which is related to this problem, but I hope I show you the difference. So if you manage, first let's call H of S the number of regions you can divide a surface so that every pair of regions share a boundary. So if S has G handles, we said this is the number. Now, and this is a homework for you. Don't do it now. And here it is. If you have a Möbius band, find a map. The maximum is 6, but find it. It's a fun problem. So these are the two problems. One is, what is the maximum regions? What is this H of S? And the other is, what is the minimum number of colors that we need to color any map on a surface so that every pair of regions that share a segment or a piece of boundary have different colors. So this is what is the maximum number of regions I can put in a map with a special property, the purple problem. The 4-color problem is, how many colors are good to color any map. These problems are very much related, but they are different. And this is just because I like it here. This is Gauss, and I'm going to read one sentence that I like very much, which he said, which is, we are in need, what we need are notions, not notations. Okay, so now we have to decide. I might be able to do all, but I don't think so. So should I move to curves on surfaces or tell the history of these coloring problems? It's a question to the...
Yeah, you can decide. Even if you take 10 more minutes or something, it's okay, I guess, since people are following and asking questions.
Are they following?
I think so. Sometimes they usually write on the chat. They may not vocally sort of answer, but they did answer a few times. So yeah.
Okay. So anybody want to ask a question? No. Okay. Okay. So let me do a quick thing about history because it's very interesting for me. So in 1840. Möbius, the same Möbius band creator, he apparently gave homework to his students, and the homework is there. He said that there was a king who had a large kingdom and 5 children, and in his will, he decreed that after his death, the kingdom should be divided among his children in such a way that the territory each should have a common boundary, not merely a point, with the territories of the remaining 4. Find the division. So he wanted each child to be able to visit a sibling without touching the land of the other. And same problem as we've been discussing. And then he said, ha, ha, ha. And why did he say, ha, ha, ha?
It's impossible.
Exactly, because this is an impossible. 5 is impossible. If, somebody mentioned the 4-color theorem, which says that if you have a map on a plane or on a sphere, the maximum number of colors you need, the minimum number of colors that you need to color it properly, so different, bounding countries have different colors, is 4. And you have to think that if you could have this map, the homework map, you need 5 colors to color it. And I hear that somebody asked me how to find the number exactly. So, well, there's 2 problems. For the problem of the regions, the idea is what I mentioned before. You have to play a little with this, a certain number you associate with a surface, which is called the Euler characteristic, and the idea and the properties of your map, and you get an equation, which is a quadratic equation, and the roots, they have to be positive. So that's a very rough sketch of the proof. Now, this was in 1840, the Möbius homework. In 1852, a student of math noticed that he was trying to color, maps of counties of England. And he said, well, it looks like, it's enough with 4 colors. And he told it to his brother. And he said, I think it's enough with 4 colors. His brother was young at that time. They were both students. And his brother was studying with De Morgan, and he told the problem to De Morgan. And De Morgan really liked that problem. He was quite interested in it. And he sent it to Hamilton. And Hamilton, the creator of the quaternions and many other things, was not very much interested in this. But it's really nice that we have the letter. Look at how he's explaining and dividing the regions. I like to see this math happening, at all times. And later, Cayley gave a talk at the London Mathematical Society, and I put a person picture. And there is the first time, if he wrote the talk, is the first time that this problem, this is the map coloring, how many colors do you need for, coloring a map, a flat map, say, whether 4 is enough for every map. And so this was 68. And then in 79, Kemper, he thought he proved it and was quite happy for a while. And he did a fantastic theorem. He proved that if you have any algebraic plane curve, something defined by polynomial equations, then there's a linkage that can draw it. An actual linkage. So something is given by a polynomial and you have a linkage. Sorry, I'm trying to play my thing again, like this one. Amazing and wonderful theorem. And then this is the idea of his proof. So, he said, well, if every region, I'm trying to give an idea of, again, I repeat, this is 4-color theorem proof by Kemper. So he said, if every region is surrounded by only 3 regions, I'll be good. Think about it. If you have a map that every region only bounds 3 other regions, the 4-color theorem, you can color that with no problem with 4 colors. But what happens if I have one region that is bounded by 4 regions? So here, he's going to try to make induction. So he's going to say, okay, I want to do something to my map and make it into a map that has 1 less region. And then my induction says that if I have 1 less region, I can paint that one, and then I'm going to do something to show that I can paint my original map with 4 colors. So if you have a map that has 4 regions, and you paint it, well, and if you try to paint it with 4 colors, and every region has a color, the region in the middle cannot be painted. So he said, well, say that I can change, the region that is green, say that I can, without messing the properties of my map, I can paint it in red. So I'll be good. I could, work with that. Now, when I cannot do that, well, I cannot do that when, if my green region touches at least a red region. But then he said, well, then maybe I can change the red and the green. But when I cannot change the red, when the red touches the green. So he said, okay, he studied the cases where I cannot change it, and you get something like this, a chain. And these are called Kemper's chain. And there, if the chain finishes, when he manages this, this region here, oh, sorry, I'm pointing the wrong place. This region here is free, and I can squish it and do some argument. Now, these are still used. This was a really good idea. And he said, well, what happens if I have something like this? here. What happens if, they are connected? Well, then I can't swap it, because if I swap it, I'm in still that position as I had before. But then I have two other colors. And then if I have a situation like this, a chain like this, well, I could join the blue and the yellow. I cannot join. I cannot have a chain join them the blue, and the yellow. So perfect. And here, this point is important because here is what I'm using that this is, we're in the plane. If I had a handle like a torus, then this would no longer be true. But here we are using the fact that this map is flat. So, this was fantastic. And, Kempe was really happy. And then, proof is done. And a few years later, he would say, oh, there's a mistake. And the idea is that the situation is not as simple as Kempe wrote it. There's a case where, when you change things, you get in, I don't have time to go into there, but you can't swap. However, he used the idea to prove that, well, 5 colors are enough. And in fact, he proved something more general. He proved that if the surface has G handles or genus G, then it can be colored with R colors, where R is the largest root of this quadratic polynomial, R squared minus 7R plus 6 times, and this number here is the Euler characteristic. So yeah, so he would put a 5-color theorem, and he uses the idea of Kempe. Now I like this thing because sometimes we do make mistakes in math, and the point is always keep progress. I mean, the proof was good. He also he said, oh, this is always equal, and this is his map of the 7-color torus, the one I showed you before. And anyway, so this is called now the Hewood number. And then he proved that this is the best bound, but this took a long time. He said, well, for genus equal to 1 torus, 7-color map is the picture I just showed you. And if the genus is 2 or more, and the number of handles is 2 or more, I'll be able to color it anyway. And it's not. It took a long time. Now, the proof of the 4-color theorem was done in 1977. As you might know, it was done with the help of the computer. These are the papers of the Haken and Apple, which are the 2 mathematicians who did this proof. These are the papers where they were working on it. You see how the graph idea appears. A fun fact is that once Martin Gardner, who's a fantastic recreational mathematician, he made an April Fool joke, and he said, oh, here is the 4-color theorem has been disproven. And he put this map, and he said, you can't color this map with 4 colors. And it's tricky to do it. You can. But, he got a lot of emails, and many people didn't understand that was a joke. He put it among many jokes, mathematical, impossibilities. But anyway, there they are. So then, Lefter did more stuff. I'm going to skip because I want to talk a little about curves on surfaces. And this is the end of this proof that, that we can color any map. We need this. Similar problem than the one I discussed in the beginning. And the solution of this one helps you solve the other one, but not exactly the same problem. This is how many colors. And speaking about this, this idea, this chain of ideas, I think is really nice because it's long and winding, with mistakes and going back. And this illustrates this says these words that were wrote by this fantastic mathematician Bill Thurston, who said, in short, mathematics only exists in a living community of mathematicians that express understanding and breath life into ideas both old and new. The question who's the first person to ever set foot on some square meter of land is really secondary. So they said that our results, I'm going here, depend very heavily on the community of mathematicians. Let me go to surfaces in my last 15 minutes. So let's move, now curved surfaces. Now we're going to think about surfaces with boundary. And here I have two pictures. This is it's a surface that we call a pair of pants. This one is the pair of pants, and it's a pair of pants of a very strange person whose lengths, and waist are, the same width. But you can imagine that you open up this, one of these boundaries, you open it up. This is, imagine, made in a very stretchy material, and use, like a Play-Doh, and you open it up until, you make it very big, and, this thing can lay flat on the floor, which will allow us to study. So now I'm going to cut this surface, and I put two cuts of different colors. The cuts are, they have to be between boundary component and boundary component, and they cannot cross each other. And as you see, I label the cuts, and I label them, this is my bad English, C-U-T, not C-A-T. So here is A, and here is A bar. A bar is the inverse that we know of, and I'm going to use a capital A because it's much nicer to type. So I cut the surface, and imagine that you physically cut, you open it up, and then you deform it into in this case, I have an octagon, and half of the edges alternated, they are labeled. And they tell me, how to reconstruct the surface. So if I read the labels, so in this case is A bar, or a capital A, B bar, and B, I get something that I call a surface word. The surface word is a ring of letters that will allow me to reconstruct the surface. So now, let's look at the surface word associated to a torus. So here, I chose these two cuts. There's not a unique way. And when I open up, takes a little time, but we get a picture like this. Again, it's an octagon, but now the surface word is A, B, capital A, capital B. And again, it's a ring of letters, no beginning and no end. So to each surface, I associate a surface word. And I'm going to skip here. And now we're going to look at curves in the surfaces, which you can think of as like a rubber-oriented rubber band winding around the surface. And we're going to deform the curves in the surfaces. So in the beginning of my talk, I talk about deforming a surface. Now we're going to fix the surface. The surface doesn't move, and the curve is formed. So here is the curve moving itself. It's a different deformations than that of the surface that I put on the right. So here I'm deforming the curve. And what I'm interested in study the curves up to the formation. So I'm going to study the classes of curves. The curves are all divided into classes, where in each class, every pair of curves can be deformed into the other. So I usually do them tight because that's the easiest way, or the more convenient way to study them. So here I have a curve, and I draw the in purple, and I draw this curve on the cut up polygon, and it's I can see better how the pieces of it intersect. Now the curve word here is, well, I start at any point because remember the curve. Oh, I'm defining what is a curve word. Sorry, curve word is a ring of letters. So here the curve word is obtained, but I start here and I get B. And then this piece, this point here that I'm pointing is glued, attached to the point here. So I start in my curve again, I go to B. And notice that I enter by a segment that is labeled by a capital B. But I'm going to record the small b. I know that every time I record the small b, the segment with the capital B come directly afterwards. I don't need to record it because I know it's there. So this is B, and then I come here, and I go to the A segment, and again, this little piece here is glow here, and then A, so I did two A's, and then I come here because it's blue here, and B. So the curve word is A, A, B, B. This can be done when I choose a tight curve, meaning like, I don't allow my curve to do something like this. It has to go, from one segment to the other always. And sometimes I'm going to write them, as the curve word, I write it as a linear word because it's very painful to be writing circles in my PowerPoint. So here I have another curve word, and a curve and a curve word. The curve word is more complicated. Here it is. Remember, curve word labels classes of curves. And I mark the intersection points. And now this is what I like to study, the intersection points. So let me just skip. This is just review. Oh, let me just tell you this. No, I would like to say it, sorry. So here, the important thing is we have two things. First, you give me a surface, and I can determine a surface word. Now, we fix a surface, and we fix a surface word, and we're going to study the closed curves on that surface. And then, fixing the surface, I have a set of curves, and I'm going to study the classes, the equivalence classes, the deformation classes of this set of curves, and each class is going to be labeled by a curve word. And there's a one-to-one correspondence when the surface has boundary between the deformation classes of the curve words and the words themselves. Sorry, deformation classes of curves. My brain is playing game this morning. Deformation classes of curves and deformation and curve words. So, and then if I want to study classes of curves, I can translate my study to curve words, and this is what I'm going to do. So let's study crosses. So here I got the same animation again, and I ask you, the audience, what is the self-intersection number of this red curve? You can read the definition of self-intersection number. The red class, the class of the red curve. What is it? I mean, here we see, in this picture, you see an example where it has 3 crosses. Here there are more than 3. Here there were 2. What is the self-intersection number of the class of the red curves? Uh-oh, I have people lost.
I think 2, right?
2? Why do you think it's 2?
If I travel along the path, I intersect itself 2 times. In that animation, you can see.
Okay, so for instance, so here, you see 2? Mohammed.
Yes.
So we count. Okay, good. That was a good guess. I mean, what I count, let me be clear, is the number of crossings. So this little point here, that's 1 crossing. Every time that I have 1 crossing, I go twice through the same point. I think that's the 2 that Mohammed is referring to.
Yeah, I think he means 2 strands are intersecting.
Right, perfect. Yeah. Exactly. So this is it, exactly. But 2 strands, every point is 2 strands. Let's count points. So in this case, it's 1. Even if, when I move around, so here, here there are 3, and here, well, there are more. Here there are 2, but the minimum is the intersection number. This is not a tight curve, by the way, the one we see now. So now, let's go back to our curve word, and let's look at the curve and the curve word that we studied before, and let's look at this intersection. Oops, sorry. Let's look at this intersection point here. So this intersection point is inside 2 pieces of curves, and the 2 pieces of curves, I mark them here in light blue. And it's here because I am going, from, this piece goes from, this edge, the edge labeled by capital A, to the edge labeled by small a. And then I want to see, well, if I look at my word here, how can I see that I will have a segment, a piece of the curve like that, going from this segment to this segment? I see because I have A. There's an A followed by an A. So every time I have an A followed by an A, this means that if I have an A, I have to enter. So in this case, I'm here and I'm going to enter in the A segment. I go towards the A segment. Oops, sorry, something moved. I go towards the A segment. And then I'm going to go here, the point that is glued, and go once more to the X segment. Now, so this is corresponds to the AA. The BB is the same. The BB gives me this segment, but every time I have an AA and a BB, I'm going to have a crossing. This red piece is a boundary. This is a crossing that I can't remove no matter how I deform my curve on the surface. So here I have another example that I'm going to skip, but I'd like to show you very quickly. No, maybe I don't. I want to say a little more math. The idea that I like to say is this, that every self-intersection, if you have a curve and you put it very tight on the surface and you look at the curve word will tell you the self-intersection number of that class of curves. And the way it is done is you're going to count pairs of subwords of the form. Well, one is this example, which is this one is AABB. That's one case. And there are cases that are a little bit more complicated, but this is the same idea, a little bit push forward. So you just count, you look at the word and you count to simplify pairs of AAs, BBs, or similar. So those are this is a self-intersection number. That's a theorem. And now we're going to use this to count curves in my last 60 minutes. So this is what I did. This, by the way, this theorem here, I should put it so you can see it. One of the wonderful things is that you can plug it into a computer. Excuse me, I need water. Meaning that I can, because there are words and there's an algorithm, I can have the computer find these pairs of subwords that count self-intersection. Which, in fact, if you want to do it by hand, but at least for me, it's almost impossible. But the computer is really good at it. So I programmed this, and I just had to play with the computer. And what I did is I made a table. So this is the table. And in the table, what I did is I classified the curves by self-intersection number and the number of letters you need to write the curve word. And I count them and I put them in the cells of the table. So for instance, here, this is the row 2 and column 1. I put how many words, how many curve words I have that represent curves with one crossing and have 2 letters. What word is how many letters? If I do here, there will be, in this cell, will be 1 crossing and 3 letters. And if I will here, will be, 2 crossing and 2 letters, and so on. And I have the computer, just go over all the words of 1 letter, count, 2 letters, count, and so on. So this is the first piece of the table. So here, for instance, 0 crossings and 1 letter. There are 4 letters. No, this is 4 words. A, B. This is, you have to think of A as a ring of letters. It's a letter of one. It's a word of 1 letter. AB, capital A, capital B. These are the ones with 0 crossings and 2. These are the diagonals. We are in the torus with 1 boundary. There are no curves that have 1 self-intersection and 2 letters. I'm not allowing, and I don't want to go into their powers of words. So AA, for some reason, I'm not allowing it. Anyway, so is this clear? Hopefully. You can ask now, looking at the chat. Okay, hopefully it's clear or totally dark, who knows. So here is the table a little bigger and even more and even more. And here I painted the curve with colors, but here is what I did. this is a row of that table. So here I have all the curve words of 8 letters. This is a row 8, and they're organized by self-intersection or crossing number. So this tells me there are 16 that have no crossings, 24 that have 1 crossing, and so on. And then, just because I was really plain, I said, let me make a histogram of this. So here I have, over each cell, I have a rectangle whose height is proportional to the number of curves I have in the cell. So here, this is proportional to 156. And you see a certain shape, hopefully, that, and here is, when you get bigger and bigger words with more and more letters. So 4, 6, 8, and then, so how does this look like? The histogram of the curve words of 20 letters. Do you know that curve?
Bell curve.
What's that?
Bell curve.
Yes, exactly. That's the bell curve, normal curve, Gaussian curve. Yes. And, when I saw this, I really jumped. I said, wow, my goodness, this is totally experimental. I mean, it looks really, really, really. And well, this is, I wrote to Steve Lally, which is a probabilist and statistician working at the University of Chicago, and he had worked in similar problems. And I said, I think this distribution, if I look at all the curve words organized by self-intersection, I think that's a Gaussian. And he answered, I said, I don't think so. So I just sent him this picture that you see here, and he answered, let's prove it. And he said that, he never saw, like from experiments, having a Gaussian so perfect, it was so strong. My husband, who's also a mathematician, said that I'm almost cheating sometimes when I prove theorems because I know they are true. Anyway, so that's a theorem that I proved jointly with Stephen Lally. And maybe this is a good moment to stop and wait for questions. It's 29, so.
Ma'am, what exactly is a deformation class?
What's the first part of your question?
What exactly is a deformation class?
It's, if you have a deformation class of a curve, is all the curves. So you give me one curve, and these are all the curves that I can deform, continuously deform into the given curve without leaving the surface. So it's called also free homotopy class, but they're all the, imagine that it's a rubber band, and, there are all the positions that the rubber band can take in the surface without leaving and without breaking it.
Okay, thank you.
No, thank you for the question. Any other question?
So for a particular deformation class, will the genus be same all the time?
Well, there's 2 deformation classes because we study curves and we study surfaces. So.
Oh, I see. Okay.
And no, but it's a very good question. And, everybody, or not everybody, many people get confused, when you're faced this time. So first you have a surface, you look at all the surfaces, and sometimes if the surface is very complicated, it's very hard to see the genus. For instance, if I show you this,
Yes.
this, it's very hard to see the genus.
Yeah.
But you know that, well, this one has genus 6, and we know that it could be deformed. When I say deformed, you have to take it a little lightly, because in fact, I need more dimensions to really deform it. But we can say it's homeomorphic, okay? There's a 1-to-1 continuous map, and the inverse is continuous, between this complicated thing and the classical thing with 6 handles that we can see clearly. So that's the surfaces. Now you fix the surface and you look at the curves. And the curves, they can be super long in a fixed surface, but the surface is fixed when you look at the curves. We deform the 2 things, but at different times. Once you choose your surface, you leave it there.
Okay.
Excuse me, madam.
Yes.
Yes, now can we know, like, ask a final question, like, what is the least length of a like a curve, closed curve in a deformation class? Like, can we
Yeah,
find the smallest length such that you cannot contract it further? So it's like a tight curve on the surface.
the length, but what do you mean by length? The length, like geometric length?
Yeah, yeah, yeah.
Yeah, that's a great question. I mean, and we usually, we have many ways of measuring length, like, because I could measure length, uh, a torus, you can think of, so you can measure length in the torus as the way you see it in R3, not just making it tight and physically measure. But you can also have other ways of measuring distances, even of spaces. Uh, so that there are different ways, and that's a very important problem that we study a lot. With different notions of distances, we put in the surfaces. We always ask, what is the shortest, what is the tightest? Yes.